Welcome to the 20th chapter on virtual substitution and real equations in the logical foundations of cyber-physical systems textbook, where we will investigate decision procedures for real arithmetic, which is a very important technology for proving arithmetic questions that arise during cyber-physical systems analysis. Now, the fact that something is challenging as first-order logic properties of real arithmetic are even decidable at all is one of the big miracles of logic on which CPS analysis crucially depends. With a black box use of the underlying quantitative elimination results, you often have a sufficient understanding of it, but not always, because now that we're looking under the hood, we will be able to understand why and how real arithmetic can be decided. And that leads us to a better appreciation for the working principles, but also the complexity challenges inherent in real arithmetic. Admittedly, we won't be able to look at everything of relevance in real arithmetic, but on the other hand, we will look at two very important cases, the case of linear equations and of quadratic equations, which there's conceptually quite elegant virtual substitution techniques for. Now, CPS analysis is very important because cyber-physics systems enable important technical concepts for building better systems around us, but their safe design requires careful specification and verification techniques. Differential dynamic logic and its proof calculus that we've discussed in parts 1 and parts 2 of this textbook does provide us with such specification and verification techniques. In theory, the only difficult problem in proving hybrid system safety is to identify their invariants, because we already have so powerful axioms and proof rules for differential dynamic logic. But, well, in practice there's additional challenges, because the additional challenge of handling the resulting real arithmetic is in theory a non-issue, but in practice quite an interesting challenge. We have seen so far only a black box use of appealing to arithmetic by the real arithmetic proof rule, which basically said, well, whenever we have something that's just real arithmetic and it is valid real arithmetic, meaning true in all states, then we finish the proof. But how does that really work? If we develop, as we do in this chapter, an intuition for not only why real arithmetic can be decided at all, but also how this works, then you come away with an understanding how you're much better prepared to identify the limitations of these techniques and learn when they're probably not going to quite work out in any reasonable amount of time, and you will get a better sense of understanding what you can do to help the real arithmetic prove more complicated properties that are out of reach for current scale technology in real arithmetic. And indeed, for complex systems, it's often quite important to use your insights and intuitions about the system itself in order to help the verification tools along, to scale up your verification results to even more challenging systems in a feasible amount of time. Real arithmetic decisions were originally proved by a seminal result from Alfred Tarski and based on logic techniques in the 1930s, which was a major conceptual breakthrough, but algorithmically quite impossibly impractical, because there wasn't even a tower of powers of 2 that would ever bound the complexity of the procedure that he proposed. But the breakthrough was a major conceptual one. Now, many years later, in the 70s, cylindrical algebraic decomposition due to Collins led to a really practical procedure. Unfortunately, also one that's quite non-trivial, so we won't be able to get there in this lecture at all. But there's also simple and elegant model theoretic approaches that understand arithmetic decisions just using logic and algebra, which are very easy to understand, but unfortunately do not lead to any particularly useful algorithms. There's also Cohen-Hermann algorithm that, well, is in between the two. It's easy enough to understand, and it does lead to practical algorithms, but only algorithms that are for very small systems, so I wouldn't be giving you a very good understanding of what's being done for larger, more complex ones. Finally, there's virtual substitution, and that's what we're going to do look at in this lecture. Virtual substitution due to Weissenfenning is a syntactical approach that fits very well with the understanding of logic that we've developed in this textbook and leads to also highly efficient algorithms. Admittedly, they only work for formulas with limited degrees, but they are otherwise a very good compromise of intuition and practicality. You already see from the fact that real arithmetic has received so much attention with so many different approaches that there's a lot to be gained there. Also, that it's slightly challenging. So what we will look at from a modeling and controls perspective is mostly an indirect impact on CPS models and controls by understanding the consequences of the analytic complexity resulting from different arithmetical modeling trade-offs. Because the point is, there's always more than one way of writing down the model. If you understand what real arithmetic ultimately does with the arithmetic, you will be better prepared for reaching good trade-offs of expressing CPS models. Because you'll have a better intuition of the working principles of the workhorse of quantitative elimination that ultimately handles the resulting arithmetic. On a computational thinking level, we'll look at how to rigorously reason and prove properties of real arithmetic. Rigorously, but also automatically, and how this miracle of quantitative elimination is possible, all by contrasting it with closely related, slightly different formulations of arithmetic that have fundamentally different complexities. We'll also be exploiting the logical trinity by the flexibility of moving back and forth between the syntax and semantics at will, which we have already done, for example, when we developed differential invariance in the 10th chapter, where we at will move between analytic differentiation d by dt and syntactic differentials, just put a prime into the term, and we moved from one to the other as we saw fit. Now we will do the exact same thing again for arithmetic, where virtual substitution is bridging the gap between syntactic and semantic operations, so in particular semantic operations that are otherwise inexpressible. And we will again switch between syntax and semantics at will to get what we want. On the CPS skills side, this lecture has an indirect impact on CPS skills by guiding and developing our intuition and insights into useful pragmatics of CPS analysis when reaching modeling and analysis trade-offs that enable us to get to CPS verification at scale. First of all, let's begin by framing the miracle of real arithmetic. What is real arithmetic? Well, here's a formula of real arithmetic which just says x squared greater than 2 and 2x is less than 3, or x cubed is less than x squared. That's clearly real arithmetic. What can we do with it? We can certainly evaluate this real arithmetic formula with logic and the reals. If we fix a state, for example, a state omega, in which the value of the variable x is 2, and then in this state we can take the real arithmetic formula, evaluate it, which will give us, of course, the 2 plugged in for x, so 2 squared greater than 2, and so on and so on. And in fact, that gives us the truth value false. Well, that was easy enough. But what if we had chosen a state nu with a different value for the variable x, namely the value -1? Well, in that case, evaluating the exact same real arithmetic formula in that state nu would have led us to -1 plugged in everywhere for x, and that then evaluates to true. So we have two very different truth values, and of course, for concrete choices of real numbers for each of the variables, it's a piece of cake, completely trivial to evaluate real arithmetic. But the point is, how do we decide whether real arithmetic formulas are valid, so true in each and every state? Well, in order to get there, let's look at a slightly different one. This formula that we've seen, now instead of asking is it true or false in a particular given state, we will ask, is it valid? So true in all of the states. And of course the answer is no, it will not be, because we just picked a state, omega, where the formula is false, so it cannot possibly be true in every state. What about this formula, the next one that is the same except it starts with for all x, is true? Well, that formula, for one thing, doesn't even depend on the state that we ask it in, because it doesn't have a free variable. If the variable x is the only one in this formula, and is bound directly by this quantifier here. So the initial value of the variable x doesn't make any difference to the true value of it. That's a good thing. But what is the true value then? It's false, because, well, this formula is not true for all x's. As we just found out up here, there is a value for x for which it isn't true. Now, what about that formula down there, where instead we have an existential quantifier in front of it? Is that formula valid? So true in all states. And now the answer is yes, because, yep, there is a value for x, as we saw a witness off here, -1, for which the formula is true. So how do we now make sure that given any first order logic formula of real arithmetic with ands and ors and arithmetic comparisons and multiplications and additions and so on, and quantifiers of the reals, well, we can say, is this a valid formula or is it not a valid formula? Let's take the validity problem for formulas and ask ourselves, for different formulations of logic, what its complexity is like. We'll ask, is it decidable? So is there an algorithm that tells us yes or no for every formula, whether it is valid or not? Is it semidecidable, which means there is an algorithm that if the answer is yes, that the formula is valid, it will tell us so. If the answer is no, well, maybe the algorithm then terminates. It's undecidable whenever it's not the case that it's decidable. And it is not even semi-decidable for when there isn't even an algorithm that on every valid example of a formula will tell us in finite time that it is a valid formula. So now, first let's look at propositional logic. Propositional logic, so the logic that just doesn't have any variables, also doesn't have any quantifiers, because you really need variables to quantify over. So it really only has things like p and q, or not p implies that q, or things like that. Well, that's perfectly decidable, right? Because you can write an algorithm that, given any propositional logical formula, will tell us whether it's valid or not just by forming a truth table with all the possible yes, no truth values for each of the p, q, and so on symbols in the formula, and then just evaluate it. It's not super efficient. There's much better ones, stat solvers, but at least it's easily seen to be decidable. Now, what about first logic uninterpreted? So we have predicate symbols p, q, r, and so on, and function symbols f, g, h, but we do not have any specific real arithmetic knowledge in it, for example. So in particular, we don't use addition, multiplication, or equality in comparisons, but we only use p and q, but we also use for all x, p of x implies q of x, for example, where the quantification domain is just any non-empty set that we don't know anything about. It doesn't have to be the reals. Well, in that case, you're talking about uninterpreted first order logic, and that's semi-decidable by seminal results due to Gödel and Urban, which means a logical formula in first order logic, if it is valid, there is an algorithm that for any valid input will give us a yes answer in finite time, in particular by also giving us a proof. But if the formula is not valid, it might just keep on trying and trying to prove it and failing, and it doesn't know whether there just isn't the proof or whether it just hasn't quite found the right proof yet. Now, first the logic where we now, instead of the predicate symbols and function symbols that are uninterpreted, we don't know what they mean, now we go to the other end of the spectrum where we just have interpreted ones, addition and multiplication and equality, for example, and our quantifiers and variables range of the natural numbers. So this is addition and multiplication of natural numbers. Well, in that case, first the logic over natural numbers is actually not even semi-decidable by a shocking result of Kurt Gödel from 1931, which means for natural number arithmetic, no matter how innocent that sounds, it's impossible to give an algorithm that says yes when the answer was yes, says no when the answer was no, or just settle for one of the two. In a certain sense, you have to be lucky in order to find a proof for natural number arithmetic. Now, propositional logic and first logic should make us semi-optimistic, although none of them were particularly amazing as soon as quantifiers entered the game, but natural numbers should make us pretty pessimistic about doing anything useful with arithmetic. Now, what happens when instead of addition and multiplication and arithmetic comparisons over the natural numbers, we look at over the real numbers, the thing we've been working with for the entire textbook? Now we're quantifying over real numbers, and of course variables will also have real numbers. In that case, due to a seminal result by Tarski from 1931, which was only published much later, unfortunately, is shown to be decidable. So there's an algorithm, it's in fact even better than uninterpreted social logic. There's an algorithm that, given any logical formula of real arithmetic, will in finite time say yes whenever, if and only if the formula is a valid formula, which is really amazingly cool. Let's contrast this with, quite close to that, virtual logic of rational numbers. So you've got fixed the same addition, multiplication, and equality, for example, but look at rational numbers instead of real numbers. Well, in that case, it might look very close to real numbers, but thanks to a seminal insight by Julia Robinson from 1949, this is not even semi-decidable. So neither when for all valid formulas, no for invalid formulas, will you be able to find a proof in any finite amount of time, except when you're lucky. And what's the reason? Why is there such a shockingly big difference between real numbers arithmetic and rational numbers arithmetic? This is awfully close. Can you guess? Well, putting it the source is easy, doing the proof is really hard. The source is that, for example, the square root of 2 is a perfectly legitimate real number, but it just isn't a rational number at all, which already the ancient Greeks knew. When you can point that out by, for example, asking whether the formula there is an x such that x squared equals 2 is true, which, or the real numbers, the answer would be yes. Or the rational numbers, the answer would be no, and in general you can't be able to always tell these apart. In fact, that crucially depends on the presence of nonlinear arithmetic to ever find such a difference. In complex number arithmetic, however, it's again decidable, also due to Tarski, but also later on Chevalier. So complex number arithmetic, so imaginary units and these kinds of friendly guys, it's again decidable. Let's write down more. This seems to be interesting. So real arithmetic, where we only look at addition, equality, conjunction, no disjunctions, not indirectly by negations either, and only existential quantifiers. What happens in this case is clearly decidable because it's a fragment of full real arithmetic, the one where we're only allowed to talk about addition, equations, conjunction, existential quantifiers, no universal quantifiers, no multiplication, no disjunction. In that case, it is decidable, but it's actually Gaussian elimination that does it, solving a system, conjunctive system of equations and asking do they have a common solution. And they're linear because you're not allowed to multiply. It's called Gaussian elimination, but the result is much older, more than 2,000 years ago. Real arithmetic that you look at like that, except you allow inequalities, then it's also clearly decidable because it's a fragment of first order real arithmetic. But in particular, it's decidable because you're asking a system of linear inequalities whether it has a solution or not, and that's decidable by a result due to Joseph Fourier from 1826, where you basically do a variation of Gaussian elimination and make sure you take care of the sign flips in a good way and things like that. Now, Natural number arithmetic, remember, natural numbers were kind of hard. Piano arithmetic is not even semi-decidable. Natural number arithmetic, but if you're not allowed to multiply, you only have additions, but you're adding additional predicates in there, a predicate that you can ask, is the number even? Is it divisible by 2? Is the number divisible by 3? Is the number divisible by 29? Things like that. Well, in that case, the arithmetic becomes decidable again due to a result by Pressburger and Skolem. Let's look at extensions of real arithmetic. Now we've seen variations of it. If we look at real arithmetic where in addition we throw in the exponential function e power x, well, in that case it's an open problem whether that's decidable or not. For nearly 100 years now, that's kind of a difficult one. If instead we throw in this trigonometric function sine function and add it into the real arithmetic, well, in that case, even though you're starting with real arithmetic, addition, multiplication, and arithmetic comparisons, and of course, and or still, the fact that you admitted the sine function means you also admitted the question of whether the sine function has a root, and whether the sine function has a root. Look at this picture. The sine function has a root here, but that's just a shifted version of the natural numbers, because, well, just multiplying by pi will give you a copy of the natural numbers. So indirectly with the sine function you would have the natural numbers, and remember that natural number arithmetic is really hard, not even semi-decidable. So that's also not semi-decidable. For example, investigated closer by Richardson in '68, but really, of course, based on Kurt Gödel's results. In other words, it's a bit of a miracle that the case we would want, real arithmetic, is so very nicely behaved and decidable. Let's understand how it works. The hammer is quantifier elimination. If we can delete one quantifier at a time to come up with an equivalent formula that doesn't mention the quantifier, then we can decide all arithmetic formulas that have a gigantic prefix of all variables being universally quantified in the beginning, because we keep on deleting one at a time by clever transformations. Let's do that. For example, if we have a logical formula, is there a y such that y is greater or equal to 0, and 1 minus x minus 1.83x squared plus 1.66x cubed is bigger than y? Well, in that case, if we're here plotting the value of this polynomial as a function of x, then basically we would like the value of this to be bigger than the value of y, but we also want y to be greater or equal to 0. In other words, we're talking about this bluely indicated set of states in the xy coordinate system that satisfy this logical formula, and now we're asking the formula, is there such a y? And yes, apparently at this point there is such a y, right? Any value in between. At this point there is such a y. At this point there is such a y. For example, that one, or also that one, just right under. In other words, such a y exists in these intervals here. Pay attention to the openness at the boundaries and so on, and that means by quantitative elimination we will be able to reduce the question whether such a y exists to that exists if and only if x is between roughly minus 0.75 and 0.68, which is describing this open interval, and it's also true if x is just big enough, if it's bigger than roughly 1.18. Now, of course, ideally we would like this quantitative elimination, which is taking us from this logical formula to that logical formula, which we now see geometrically corresponds to the question of projecting this region down to the x-axis. We would like this to become algorithmically possible, as opposed to, well, plot a picture of this and try and draw and figure it out somehow to reduce it to this question. In fact, observe if all except one variable already has a fixed real arithmetic numerical value, then the only thing you're dealing with in here are univariate polynomials, polynomials that only mention one variable. And for univariate polynomials, it's kind of obvious that here we will have as an answer a finite union of intervals, because univariate polynomials only have finitely many roots. For example, here it is 0, here it is 0, here it is 0, but not more often. And it cannot possibly have more roots because it is a polynomial of degree 3, and I can have at most 3 roots. This one does have exactly 3 roots. And because if we only have univariate polynomials, all of them can only change signs in finitely many places, which means the answer, even though it might be hard to construct, must be of the shape that it's a finite union of intervals, which is one of the defining principles that we will be using. Now, there's a lot of duality between polynomial equations and the geometric shapes that they describe. They describe things that are known as algebraic varieties. For example, here in the plane, you've got the set of all points where x cubed is y. That's precisely this curve. Here's the set of all points where x squared plus y squared is 1. That's precisely the circle. Here's the set of all points where y squared is x squared times x plus 1. That's this cute curve. Here's the set of all points that describes this funny equation. Here's the set of all points in 3 dimensions that describes the identity that z equals x squared minus y squared. Which means conjunctions of polynomial equations actually define algebraic varieties, which are directly the geometric counterpart of the polynomial equations we're writing down here. And likewise for inequalities. For example, this blue region here is the set of all points where the absolute value of y is equal to the absolute value of x cubed. Absolute value, wait, that's definable by, saying things like, if y is negative, then the absolute value of y is minus y, and if y is greater or equal to 0, then the absolute value of y is y, and likewise over here, and x times y is greater or equal to 0. Here you've got the solid disk, the set of all its points where x squared plus y squared is less or equal to 1, so including the circle, but also any point in between. Here's the set of all points where y squared is x squared times x plus 1, and x is at most 0.44. That's this region, but not over here, for example, anymore. This blue region corresponding to that. So, in other words, polynomial inequalities, which are logical, correspond geometrically to what are called semialgebraics. It's their finite unions and intersections of these single polynomial inequalities, for example. Here's one. And now it turns out, which is a seminal result of Tarski from 1931, that first the logic of real arithmetic, with which you can describe all of the sets that I just talked about, is decidable because it admits quantifier elimination. That means for every formula P, one can compute a quantifier-free formula that denote quantifier elimination of P that is equivalent, meaning the formula P equivalent to the quantifier elimination version of P is a valid formula of real arithmetic. And there's one algorithm that for every formula P of first logic of real arithmetic will produce as output a quantifier eliminated version of it. Now, of course, this is not unique because you can just change the formula QE of P arbitrarily to preserve the set of all states in which it is true. For example, by tagging on an or false at the end, or tagging on an and true at the end, which doesn't change it. But it's a miracle that this is possible. Now, that was the good news. The bad news is that the complexity is not so amazing. I already told you that the complexity of Tarski's original seminal breakthrough result was non-elementary, so no power of 2s would have bounded the complexity of it. But a much more practical procedure and results by Davenport-Heinz, and in particular also Volker-Weisspfenning from '88, show that the time as well as the space complexity of cognitive elimination for real arithmetic is much better than that, but still kind of bad, namely doubly exponential in the number of quantifier alternations. In practice, often doubly exponential in the number of quantifiers, unfortunately. And in particular, Weisspfenning showed that this is the answer of the only description of the quantifier-free form, even if you have just one free variable and even if you only have linear polynomials. So doubly exponential it is, which isn't amazing. But what is amazing is it's possible at all. And what's also useful is that oftentimes we ask closed formulas, the ones that we just would like to decide instead of computing a criterion under which it would be true. Let's practice this a little bit. What does quantifier elimination have to do? If we ask, is there an x such that 2x squared plus c is less or equal 5? Well, can we express that without the quantifier? Yes, because the best version of the quantifier would be just drop in 0 for x, because that certainly makes it less or equal 5, if possible at all. In other words, this is equivalent to just asking whether the value of the variable c is less or equal 5. Now, if we ask, for example, a formula like, for all c there is an x such that the same thing again, well, then I guess we could ask, can we quantifier eliminate the result of already having quantifier eliminated the inner quantifier exists? We can eliminate one quantifier at a time. Now, the inner one we just computed is equivalent to c less or equal 5. So the question, what the formula for all c less or equal 5 is equivalent to, can you rephrase that? Sure you can. Well, let's just make it easy. C could have all kinds of possible values. We could have the value minus 100, so minus 100 needs to be less or equal 5. It could have the value 5, so 5 has to be less or equal 5. It could have the value 100, so 100 needs to be less or equal 5. And yeah, admittedly, for many more real numbers than the 3 we chose, but the point is that if we just find sufficiently many of them in the argument why you've quote-unquote covered them all, then you found an equivalent version of it, because you have already found out that 100 isn't less or equal 5 anyhow, so the formula certainly will be false. Because, yeah, not every number c is less or equal 5. You know, I've heard of 17, for example. Another example. Quantifier elimination for there is an x such that a equals b plus x squared. Well, can we say that without the quantifier x? Well, x squared will certainly be greater or equal to 0, and whatever difference a and b have, we can always make up for that by choosing the appropriate x if and only if a is indeed the bigger number. So that's exactly equivalent to just saying a is greater or equal to b. Is there an x such that x squared is 2? No, that's equivalent to true, because, yep, such an x exists, but now we haven't learned what it is. However, the similar formula, is there an x such that x squared is 2? Oh, and that x agrees with the value of y. We'll now, of course, have to characterize exactly what the value of y is. So that would be y is the square root of 2, or minus the square root of 2, because these are the two solutions of this. And well, depending on your perspective, that's fine or not. I mean, it's not really fine, because we didn't officially admit square roots just like that into our language. So we could have stated that differently by, for example, saying y squared is 2 is a formula that is equivalent to this formula. And that's all we need for this result. Now, what can quantifier elimination do systematically? Well, first of all, let's do some simple logical normalization. If we're asking to quantifier eliminate a formula that starts with an AND, well, of course, we can just quantifier eliminate the left-hand side and the right-hand side and, conjoin them back together. Likewise, if we ask quantifier elimination for an OR, we can eliminate the quantifier separately and put the OR back in. For a NOT, we can quantifier eliminate the formula A, and so it comes back with a formula that has no more quantifiers anymore, and then we put the not in front of it again. For all, we can ask quite cleverly to instead quantifier eliminate the equivalent formula, not there is an x such that not A. Well, why? Well, because that will make the not go away and will enable us to focus just on quantifier elimination for existential quantifiers. If we know how we handle quantifier elimination for existentials, we also understand how we handle quantifier elimination for universal quantifiers. Now, of course, that means we should be doing something clever about the quantifier elimination of existential quantifiers. Now, well, I can still do one thing that's not quite so clever. If A has any more quantifiers, we can first apply quantifier elimination to the inner thing, and when we're done with that, apply quantifier elimination to the result of that. But at some point, of course, we really have to quantify or eliminate for real. There's a few more tricks we can play. For example, we can say quantify elimination for there is an x such that a or b. Well, there is an x such that a or b is actually equivalent to there is an x such that a or there is an x such that b, so we can split it into two different quantify elimination questions. Likewise, we could also, if we have a conjunction with a negation in front of it that we can distribute by De Morgan's laws and make it easier. Likewise, a negation over a disjunction, we can apply De Morgan's laws to that, and we have a double negation. Of course, we can make it go away. In other words, we could always normalize the formulas and split over disjunctions. Also, we can use distributivity if we find A and B or C. We can expose the disjunction by, well, unfortunately, copying the formula A a bunch of times. Likewise, we can distribute in the other way. The point is that after these transformations, we can always, although at a bit of a cost, look at a normal form where we say if only we succeed in performing quantifier elimination for existential quantifiers in front of pure conjunctions of atomic formulas, then we're done because the rest of the transformations can handle the other logical operators. So that was logical normalization, but we can also peek into the atomic formulas and do a bit better. For example, if we have an equation P equals Q, we could instead look at P minus Q equals 0 because it's a bit easier just to worry about having 0 on the right hand side. Likewise, of course, if we have greater or equal, we can pull it on one side. And for example, what we can also do is whenever we have, for example, not greater or equal, we can say write P is less than Q, and if we have not greater than, we can write less or equal to, and so on. In other words, we can just arithmetically normalize the question because it doesn't change the pseudo states where it's true, to assume without loss of generality that quantifier elimination only needs to handle existential quantifiers of conjunctions, of comparisons that are only these, greater, equal, greater or equal, not equal, with polynomials on the left-hand side and exactly the 0 polynomial on the right-hand side. If we handle these, then the rest of the logical and arithmetical normalization can handle the rest. But of course, ultimately, we really need to do this. So let's do it. We eliminate quantifiers by virtual substitution, basically by saying there is an x such that f is equivalent to putting a number of terms, concrete terms from some set T, into the formula and maybe conjoining some extra quantifier-free additional compatibility conditions. So one thing is clear. If for T we would use the set of all real numbers, then the two sides, if we just drop this thing, the two sides would be clearly equivalent, but because there is an x such that f is equivalent to, f of T for any real number T, but the problem is that then the right-hand side would be an uncountably infinitely big formula, which really isn't a finite formula at all. So we have to make do with just some smaller set of concrete points we plug in a certain sense. But at least this side always implies that because these are all concrete witnesses. The trick is the other way around. The trick is to show that if we have plugged in a number of concrete terms for x, then if f wasn't true at any of them, f isn't true for any value of x at all. Let's make that happen to make sure that on the left-hand side we have a quantified formula, but on the right-hand side it is equivalent to a quantifier-free formula. How can this work? Well, let's first naively do virtual substitution in a simple example. There is an x such that x is greater than 2 and x is less than 17 over 5. Well, of course, we could compute the answer to that somehow, but if we're trying to be systematic about it, well, this formula apparently is mentioning the number 2, so maybe that's the answer. It is also mentioning 17 over 5, so maybe that's the answer. 2 and 17 over 5, but of course these are not the only points where the formula could be true at. It could be true, anywhere else as well. So basically we will take this formula and rephrase it to, well, maybe it was the boundary case 2 because it's been mentioned there that does it, and the answer is no, because 2 isn't bigger than 2. Or it could have been the other boundary case because it was mentioned there, 17/5, but 17/5 also doesn't do it. Or it could be an intermediate point, a point in between the two. In fact, it could have been any point in between the two, but how about we choose exactly the midpoint, the sum divided by 2. Maybe that's the one. Well, or it could have been, a point that's bigger than 2, could have been a point over here, or it could have been a point down there. So, for example, the minus infinity is sort of the extreme case. It could have been a really small value, or it could have been a really big value. And now the trick is, of course, to argue these instances are all reasonable instances, but why have we covered them all? In this case, we can evaluate and say, that's false, that's false, that's false, that's false. But this one is true, so the whole thing is actually true formula. That's the good intuition, but of course it comes with a number of challenges. First of all, this infinity thing that we talked about isn't really in the first logical real arithmetic because it isn't even a real number. The interior points that we need here aren't always actual direct terms. We have here just the midpoint. For higher degree polynomials, it gets more complicated than that. And also substituting them into formulas does require more attention than we have devoted here. Let's get more systematic by looking at special cases. And then ultimately working back with an understanding why we've covered quote-unquote all of these special cases. For one thing, one of the formulas that we have at hand could have been a linear equation, b times x plus c equals 0, and other conditions. Well, this conjunction can only be true if the left-hand equation is true, and this equation can only be true if, precisely, x is the appropriate solution for this linear equation. In particular, the whole formula is true if and only if this one unique solution for this equation plugged into f works. So that means if we substitute the solution minus c over b for x in f, then we found a formula that is equivalent to the question whether there is an x such that the linear equation in f is true. Good. And now, of course, division requires care. We really shouldn't be doing that if b is 0, right? Because division by 0 has all kinds of funny values, but we don't know which one. So it is equivalent to that if b is not 0, which in general we can't really know, because we don't know what shape the term b has. Speaking of which, the whole thing, the whole equivalence is only true if b indeed is not 0, because if b is 0, then here we have a equation that says c equals 0, and that really doesn't tell us a whole lot about what the right value of x is, because it's independent of it. But we still have a conditional equivalence. If b is 0, then that's precisely the answer. In fact, of course, it really only is a linear equation if the variable x doesn't actually occur in the terms b and c. Otherwise, if b is, for example, 2x, then secretly we have had a quadratic equation, not a linear equation. That would have been very different. So we have a conditional equivalence in this particular case, which means occasionally we may have to split the cases and say, well, I don't know whether b is 0 or not because it's another polynomial in a variable y. Could have been y squared minus 1, and I can't ahead of time say whether that could be 0 or not. So when in doubt, I might have to distinguish cases and say, good, there's two cases, the one where it is 0 and the one where it's not 0. The condition that the variable x that we're quantitatively eliminating doesn't occur in b and c is, of course, an annoying side condition, but we can easily get rid of it in the uniform substitution formulation. Here's a uniform substitution axiom, remember chapter 18, where if b and c are arity 0 function symbols without arguments, then b not equals 0 does imply that there is an x such that b times x plus c is 0 and q of x is true, if and only if q is true of the one unique solution that we've got, minus c over b, which is well defined because of this assumption. And remember that uniform substitution will not allow us to plug in for b or c terms that mention x, because x is already bound here. So This axiom is easily proved to be sound and precisely performs the virtuous substitution of linear equations. For example, it will give us this instance because y squared plus 4 really is easily proved not to be 0 ever. It's positive. That there is an x such that y squared plus 4 times x plus yz minus 1 equals 0, and x cubed plus x squared equals 0 by just plugging in the one unique solution for this, which is this division minus yz minus 1 divided by b into this right hand side, and so we just are left with the condition that says this solution cubed plus this solution is greater or equal to 0. Very easily done. Let's do the same thing just for higher degree polynomials that are no longer linear. For the quadratic equation case, the question, is there an x such that ax squared plus bx plus c equals 0, and f is true, can also be rewritten equivalently, sort of in a similar style. How do we do that? Well, again, if a conjunction is true, well, both of the conjunctions need to be true, and in particular the left-hand side conjunction is only true because it's an equation for, well, the solutions of this particular quadratic equation. What's the solution of this quadratic equation? Ax squared plus bx plus c. Yep, precisely. It's the square root. It's minus b plus the square root of b squared minus 4ac divided by 2a. You can also sometimes remember that by actually dividing by a and putting it here and there, which will give you the same thing. So if we plug in minus b plus square root of b squared minus 4ac divided by 2a in for x, then that's precisely the solution for this quadratic equation. Hold on a minute. How many solutions do quadratic equations have? Well, it kind of depends. It could have had two solutions, so maybe it is not plus the square root but minus the square root, because look at this quadratic polynomial. Equals 0 has two solutions, this one and that one. So we should plug them both in, but logic can do that for us. It can just say or. This is true if and only if that or that is true. Now, of course, dividing by 2a is a lot more fun if we only knew that a isn't 0, right? So this thing only actually works out this particular case if a isn't 0 and the other things, because otherwise dividing by 0 isn't a good idea to do. But also, what else could go wrong? Well, the square root, right? Does the square root exist? Square root of minus 1 exists, but not in the real numbers, only exists in the complex numbers. And when we're trying to eliminate quantifiers in the real arithmetic, we shouldn't be using imaginary numbers as witnesses. That doesn't work. So that square root only exists if the discriminant b squared minus 4ac greater or equal to 0 is actually true, which makes some sense because this polynomial has roots, but for example, had we looked at this polynomial instead, it just wouldn't have had any roots at all. It wouldn't have satisfied this condition that there's any roots at all. Of course, the polynomials could also touch and only have a single root. That's also a possibility, but in that case, just a positive and negative square root would have been identical, because the discriminant is precisely 0. Of course, that means, however, that, well, if instead a is 0, which again, in general, we can't know whether it will be or not, because it could be a polynomial and other variables. If it is 0, then an entirely different solution is the one, because the solution of a quadratic polynomial that starts with a leading coefficient 0 is really secretly a linear polynomial, in which case it has one solution, but that case we already understand. So if a is 0 but b is not, then minus c over b is the right solution for it. And we just form the disjunction of the two cases, because in general we can't quite know which case we're dealing with. Now we've got an equivalent formula. Almost, right? We almost have an equivalent formula. There is an x such that ax squared plus bx plus c equals 0, and f is true if and only if, having plugged in the one linear or the two quadratic solutions into f gives us a true formula under the appropriate compatibility conditions that the divisions and roots are defined at all. But the whole thing, of course, is only really equivalent if this equation was a proper equation. Indeed, if a isn't 0, or b isn't 0, or c isn't 0, so the whole thing doesn't completely trivialize. Only then are the two equivalent. And otherwise, well, what if all A and B and C are possibly 0? That is more annoying, but then we basically look through F to see if we find a number equation that we can handle. A similar decomposition with that gives us case splits. So if cofactors could be 0, annoying things happen, but they can be dealt with in principle. Good. Of course, the whole thing only really works if A and B and C again are really not mentioning the variable x again, because otherwise it wouldn't actually be a linear quadratic equation. All it would just have been an inappropriately written down higher degree equation. So we have now, under these conditions admittedly, a quantifier-free equivalent to the blue formula here, which is great. The problem is just on a formula, because we're talking about square roots of big and complicated polynomials here. Square roots are not in our official syntax. Can't just be using them. And in fact, even division is a bit of a questionable thing, right? It's not in true core first the logic of real arithmetic. So we need to do something about that. And here comes the trick. Now what we do is, it's still an equivalence, right? We're just not allowed to mention these terms syntactically. If we define a virtual substitution, an operation that pretends to plug in these square roots and divisions into formula square roots of the generic shape a plus b square root of c divided by d. In this particular case they look like that, but that's less important. If we define a virtual substitution that pretends to plug these square roots and divisions into logical formulas without literally actually doing it, but giving us just back a formula that's equivalent to the formula that we would have gotten if only we would have been allowed to use those square roots and divisions, well, then we're in business. So virtual substitution is a pretend to substitute but rephrase right away kind of operation. And the notation for that is that I use a little bar on top of the variable to indicate that yes, we're doing this substitution, but we're not taking it quite so literally, but we are substituting it virtually. And that's what we will now develop for these square roots, which indirectly also has handled the case of divisions that we need along the way. For example, we could certainly give back a formula that's equivalent to having plugged in square root of c by saying there is an r such as r squared c, because that's precisely the values for which that agree with the square root of c, the positive or negative root. Except the problem is now we're using another quantifier, and it wouldn't be very clever to eliminate a quantifier by here adding another quantifier back in, because then we would be going in circles. We have to do this without mentioning quantifiers. So let's go there. Let's develop the virtual substitution for these square root expressions. If we start at the basics, how would we substitute a square root of expression a plus b times square root of c divided by d for terms a, b, c, d into a polynomial p? Well, a polynomial, well, that's syntactically just a bunch of additions and multiplications, right? So in other words, if we figure out how to add and multiply expressions of this shape, it's very easy, right? So if you plug in the a plus b times square root of c over d into a polynomial, we're just evaluating the additions and multiplications in it. How? Well, by wondering if we have one expression plus another expression of the shape, what's the symbolic square root of expression that we get out? Careful, on this particular slide, prime does not mean derivative, unlike anything I ever said before in class, just because otherwise I would introduce too many complicated names. So just read prime as a prime. It's just another variable name a, right? So a b prime is just another term, possibly different from b. Okay, now if we're given this expression and that expression, and they share the same square root of c on both of those sides, well then it's easy to add them just by, what do we need to do? We're adding two fractions by multiplying up to make sure that they have the same denominator. So we give the two of them the denominator d times d prime, and then multiply this up by d prime to make that happen, and multiply this up by d to make that happen. In other words, we have a times the d prime that we wanted, and over here we have a prime times the d that we needed, right? A prime times the d. Then we have the b times the d prime that we need here, and the b prime times the d that we need here, times square root of c, because they share the common factor square root of c, and the whole thing is now divided not by d or by d prime, but by the product d prime, which certainly is the right answer for that. So you just symbolically compute, in other words. Do we do it for multiplication? Well, like that, except we don't need to bring things artificially and on top. We just like multiply the tops and multiply the bottoms, right? So that will also give us dd prime, right, just by having multiplied that. But now we multiply this with that, and that certainly gives us a times a prime, and it certainly gives us a prime times b as a cofactor for square root of c, and it gives us a times b prime as a cofactor for square root of c here. But what happens with the b square root of c times b prime square root of c? Well, that gives us b prime, but it gives us square root of c times square root of c, which is, last I checked, I guess, c. So that is b times b prime multiplied with c as a factor here. And of course, the whole thing really is actually okay and well defined if we made sure that the division that we had here and there wasn't dividing by 0, and the square root had better exist, so c had better be a value greater or equal to 0. What that means, essentially, we're just symbolically computing with these expressions by adding and multiplying them up completely symbolically, which gives us a way of plugging them into polynomials. Well, next question. If instead of a polynomial, we have a polynomial comparison, so think of this as p equals 0, or p greater or equal to 0, or p greater than 0. How do we plug in a square root expression for the variable x virtually? Well, first of all, we can certainly first evaluate the polynomial. We just evaluate its plus and times arithmetic by plugging in a plus b square root of c over d for x and that, but we need to then do something slightly clever to handle the arithmetic comparisons, and this is how we do it. If the result of that is, for example, of the shape a plus 0 square root c over d, so in other words, it's just a division a divided by d, and we would like to compare that to 0 without mentioning the division, how can we do that? Well, a divided by d equals 0, of course, that's true if and only if a is 0, right? And a divided by d is less or equal to 0, well, if a is less or equal to 0, well, unless d had a different sign, in other words, the whole thing is less or equal to 0, actually, if and only if I'm sneakily multiplying them, I get something less or equal to 0. Likewise, a divided by d is less than 0. Well, that depends on the sign of these things, but that's precisely equivalent to a multiplied d is strictly less than 0. And likewise, the other cases are slightly more complicated. If we actually have a true square root expression in it, so it's an arbitrary polynomial term b, then we need to be slightly more clever about it. For example, the ideas from up here do work, but it still depends. So a plus b squared c over d could also be 0 because the two things cancel out. So for example, if a times b is less or equal to 0, that means a and b have opposite signs, but their squares are equal. So a squared is the same as b squared times c, which is the square root of c. Then they have the same absolute values, but they have opposing signs. So of course they cancel and give us a 0. It's more arithmetic, but it's still not mentioning any square roots, not mentioning any divisions. For a less or equal to 0 comparison, if we have these square root expressions, and we're asking, is it less or equal 0? Well, then we sort of proceed like that. So first of all, if a and d have opposing signs, then we're in pretty good shape. If we make sure that the absolute values of this side and this side are pointing in the right direction, so if the magnitude of a is greater than the magnitude of the other side, so a is the dominant value here, but a and d have opposing signs, but it could have been the other way around as well. So it's also true whenever this is the dominant sign, so whenever b squared c is greater or equal a square, so this one wins over that one, and now the sign of this b and that d are opposing, so b times d is less or equal 0. Then it's also true. Now, for the strict comparison, it's even slightly more complicated. Again, if a dominates over this, which we can find out by asking their square, so if a square is greater than b squared c, is a way of reading that, and they have opposing signs, so it's not just because of the squares, but it's that a times d has the appropriate sign less than 0, then this squared expression is true. But also if, now it gets a bit more complicated, if these two have opposing signs, so b and d already dominates, and it is either the case that a and d have strictly opposing signs, so even if this could have been 0 still, a and d give us a value that guaranteed isn't 0, or if it's not the case, then at least the absolute value that we get here, a squared, compared to the absolute value we get here, the one that we characterize by writing down b squared c, satisfies the appropriate strict less than relationships. So admittedly, you need some thought to figure these things out, but the point is that all of those cases give us formulas that pretend to have plugged in the square root, but never actually really seriously did. Also notice, if it's just division, the result is not so bad, it's pretty tame, but if it's actual square roots, then we get a lot more duplication. In particular, square root equations are not so bad yet, but square root inequalities give us more disjunctions behaviors. And of course, a lot of the resulting arithmetic can be simplified substantially if we just know a little bit about these sign conditions and can rule them out eagerly ahead of time. So if all kinds of things could be 0, it's more complicated than if it couldn't. And well, now that we've figured out how we compare a square root polynomial expression with 0, we can of course also do the same thing for and or formulas, just by keeping the and ors around these expressions. And now what we have defined is an operation that pretends to plug in a square root expression a plus b squared c over d in for x into the logical formula f, without literally doing so. It gives us back a formula that's a virtual substitution analog of that, which is equivalent, but it didn't literally mention any of the square roots or divisions. In other words, here on the left-hand side, we're dealing with an augmented logic that is extended syntactically to admit square root and division expressions that usually aren't part of what we're talking about syntactically. But on this side, we really have pure first-law logic of real arithmetic without syntactic extensions. And the point is that the two are equivalent. And more formally, that says that the left-hand side formula f is true in a state omega where the value of the variable x is chosen to be a real number r, if and only if, in this state, the formula on this side is true, the virtual substituted one, where the value r, which is a real number that we're plugging in, is precisely the real number we would have gotten had we computed the value of the square root expression that we're plugging in. So it's the value of a plus the value of b in this state multiplied with the square root semantics level of the value of c divided by the value of d. And of course, these things are true only if the square roots are well defined and the divisions are well defined, but that's precisely what the rest of the formula is already checking. We're only using this division by b if b wasn't 0, we're only using this division by a if this a wasn't 0, we're only using the square roots if the discriminant is actually greater than 0, so only if the square root is actually well defined. Now this is the move between syntax and semantics at will lemma for the virtual substitution that we use in order to cover the case of quadratic equations. So let's just try what happens when we use this virtual substitution principle for quadratic equations in a simple example. So we have that a isn't 0, so whenever in our quantified formula we have ax squared plus bx plus c equals 0, it's a proper quadratic equation. We don't have to worry about it possibly degenerating into a linear equation because a could be 0. And then we ask whether this formula here, the solution of this one, is true in essentially itself again. So where the formula back here in the polynomial has the exact same polynomial. And then of course, what we should expect that if we plug in the solution of this quadratic equation into itself and ask whether it's less or equal 0, that the answer will come back as a true, and the only remaining condition is that there really was a quadratic solution to begin with, which means that the discriminant of this polynomial is squared equal 0, so b squared minus 4ac squared equal 0. Let's just convince ourselves that that's actually really the case by asking what happens if we plug the quadratic solution of the blue polynomial into the red polynomial, which of course is the same. Let's do that. In this case, we just symbolically evaluate ax squared plus bx plus c by just writing ax squared, but that's this thing, plus b times x, that's this thing, plus c. Now this squared means it multiplies with itself, which gives us a bunch of cross terms. So for example, minus b times minus b is b squared, plus this comes up as b squared minus 4ac from the two square roots being multiplied with one another, and then the cofactor of the square roots is 1 minus b from the one side, and from the other side another minus b, divided by, well, 2a multiplied with 2a, which is of course 4a squared. Back here, we just multiply with the b through everything, so the b times minus b gives us minus b squared. B ends up as a cofactor for this, and we leave the division alone, c is unchanged. Now, a multiplied with this, of course, just means we multiply a in, so it's ab squared plus ab squared plus a multiplied with this gives us 4a squared c, and likewise a appears everywhere. Denominator is unchanged because this one has denominator 1 implicitly, of course. That's unchanged. Now we add, for the same square root expression, something division 4a squared and 2a, which means we're ending up with the multiple 8a cubed. And this side we multiply with 2a, and that side we multiply with 4a squared, which gives us this ab squared multiplied with the 2a we get from here to give it to the same denominator, this multiplied with the 4a squared that we need here, and then the cross terms, which end up 2a from here and 4a squared from there. Now we've got a lot of polynomial arithmetic, but we can just evaluate and cancel things out. For example, ab squared times 2a gives us this, but ab squared times 2a also gives us that. We could have canceled it earlier, honestly, but now we notice that we can cancel it after factoring it out. This gives us that, which cancels with the 2ac plus 4a squared over there. And the whole thing cancels, and the whole thing cancels, which gives us, after simplification and multiplying the polynomials out, 0 polynomial plus 0 polynomial times these things. And of course now, if all the cofactors are 0, it's not like the denominator is quite so important, and we could have equivalently written 1 here. It's also not really important what the square root is, so let me just abbreviate this to dot dot, because all that we're talking about here is the number 0. And now, if we plug in this square root into an equation, for example, we would find out that it's after this evaluation, it's just a 0 number. And comparing the 0 to 0, of course, even if we do the constructions, will give us 0 times 1 equals 0, which is very simply true because 0 times 1 is 0 indeed. And if we plug this in for less or equal comparison, we will get 0 times 1 is less or equal to 0, which is also very much true. In other words, here we will get back the value that we expected at the end. However, of course, that would have been different had we had a strictly less than comparison, because then down here we would have had a strictly less than comparison, strictly less than comparison, strictly less than comparison, and 0 strictly less than 0 just isn't very true. So that would have given us a false, which would have given us a false up here. So that was just following a quadratic curiosity of what happens if you plug the quadratic solution of a quadratic equation into another formula characterizing the same solution yet again. What happens if we plug the quadratic solution that we now have a lot of practice with into a different formula, namely the 1x squared equals 0. In that case, x squared equals 0 by the arithmetic formulation, the normalization will be turned into minus x less or equals 0. And then we plug the quadratic solution that we have already computed up there into this, which, comparing this to 0, will give us, well, the b over 2a, which gives us b times 2a less or equals 0. So this has the appropriate sign, and the b side dominates over that, which gives us b squared minus this thing square, which is just b squared minus 4ac. Multiplied with all the cofactors, or likewise in the rest, which after polynomial simplification will give us this condition here. So this just gives us 4ac greater than or equal to 0, because gathering the minus and the minus gives us the plus, and the square goes away. Here we have minus 2a less or equal to 0, and these again cancel, and we have 4ac less or equal to 0 as one of the conditions that we get from having plugged in the negative square root. Plugging in the positive square root correspondingly will give us that condition. And so the whole formula here that's quantified has a non-negative solution of a quadratic equation, if and only if, well, there is a quadratic equation that's solvable at all, otherwise the equality will not work out. And then the two completely symbolic conditions that characterize that the solutions will have the appropriate signs that we want, the green, the negative root from here, and the blue one from here for the positive square root. Summarizing what we've seen is that virtual substitution works very algebraically. We plug in a square root, which we compute as symbolically the right solution for a quadratic equation, or a division, which we compute symbolically as the right solution for a linear equation, into atomic formulas by evaluating the polynomials themselves, which are just addition and multiplication, which we evaluate by algebra, like so. Of course, we can memorize these principles once and just compute them over and over again in a reasoning tool. And then we compare them here for equal 0, less or equal 0, less than 0 by making sure we don't mention the square roots again literally, by asking, for example, if a and b have opposite signs, but a has a larger magnitude, so squaring things up, a squared minus b squared c gets rid of the square root of c we would otherwise have to mention, and likewise for the other cases, which then enables us completely logically to equivalently reformulate the existence of a solution for a quadratic equation and another formula by plugging in the linear and or the two quadratic solutions into the formula f virtually, as we've just seen, by rewriting it on the go to make sure we don't mention literally these square roots and these divisions anymore, and doing everything in a context where indeed the divisions are well defined, so the division wasn't 0, and we were talking about the linear solution of an equation at all, and it was a proper quadratic solution, and the solution is well defined, so the square roots are well defined, which gives us a very logical way by changing in syntax things around equivalently that are preserving the semantics of what would have happened if only we had literally plugged in the actual quadratic solutions of equations into the logical formulas. Now, of course, after we've seen how to handle one of the quantifiers, we can just handle multiple quantifiers by basically going inside out. For example, to first make sure that f, if it has still quantifiers, we first handle the quantifiers with an f and then propagate out. and have a one quantifier here. Should there be another quantifier around it, now we've got quantifier-free formulas that we can handle instead to quantify eliminated. Now the degrees might go up, remember, because a quadratic equation which will give us a square root solution, but the square roots will be transformed away again to lead us to quadratics. And because we're multiplying things up, for example, with the denominators, the degrees might actually increase along the way. Now we know how to handle the equality case of linear and quadratic equations. Of course, there's other logical formulas as well. First of all, higher degrees that we might not get around to, but also quadratic and linear inequalities that we will be handling next time.